Let's jump into the equations for the zonally averaged atmospheric model. We are going to directly steal the equations and the construct from Holton's wonderful book, which is a classic. Basic equations are simplified by the use of log pressure vertical coordinate z. Specifically, we write the zonal momentum equation, the pressure gradient written in terms of geopotential. In the atmosphere, because the fluid is compressible, density is an inconvenient variable. So often we use the hydrostatic equation to switch to the pressure coordinate, and then we use the ideal gas law to go to temperature and replace density, which is cannot be measured directly anyways, and that's what gives us things like thermal wind relation, etc. Okay, makes it very much more elegant and easier to derive solutions. So here we are looking at the zonally symmetric solution. This is our material derivative, total derivative, of course, Coriolis term, and some frictional forcing is retained, which we will carry in some form as we do the linearization and averaging and so on. And the meridional momentum equation, again, the inertial terms, Coriolis, pressure gradient, and frictional force. The hydrostatic balance is written again in terms of geopotential. Z here is related to the pressure, so it's indeed in the log pressure coordinate. G is our scale height, again given by this expression that we have seen a few times. We have the continuity equation, and we have the thermodynamic equation with the diabatic heating term that is retained here. We'll see the impact of heating on eddy fluxes and so on in a little bit. Of course, here our total derivative is partial time plus u partial dx, v partial dy, and w partial dz, where w is now in this log pressure coordinate. So for any quantity alpha, we can write it in terms of the zonal mean as we had defined in chapter 1, where the zonal mean basically takes out the longitude and integrates around the sphere 0 to 2 pi d lambda, and alpha bar in the time would average over t1 to t2 and give us time would be gone. We would look at climatology, for example. Okay, so in that case we can write any quantity alpha as the zonal mean plus a variation around the zonal mean. Okay, this is not alpha times lambda, this is alpha star. The symbol got displaced. Nonetheless, so now you have eddies as variations around the zonal mean. So you have the zonal mean, and then you have variability around it, which we call eddies, which are varying in time and in space, obviously. That allows us to write quantities like UV, momentum terms, and temperature advection terms in terms of zonal averages and the eddy terms. Of course, here terms like U star V, zonal average V, do not contribute because by definition the zonal means of these eddies are 0, right? If we go to this relation, when you integrate the integral of this in the zonal direction would be 0 by definition, because it's the deviation from the zonal mean. In that case, the U star lambda phi z t can be written as a stationary eddy term. So we will not define it very rigorously here, but essentially, let's say the storm track is coming off of Asia, then it has a stationary part and then it has transient part. So we will split the eddies as deviations from the zonal mean into a stationary part and a transient part. Okay, even though T is carried here because the stationarity can be just seasonal stationarity. For example, the winter storm track can create something that's anchored to the land coming off of Asia or North America and so on. So I'm being moving back and forth. We are in the tropics, but even in the tropics you can have stationary eddies happening. So sticking to the mid latitudes, what are we trying to do? Essentially, we're trying to look at how the eddies have to be oriented to be able to transport momentum and heat northward. What is the main idea? We have excess energy coming into the deep tropics. We have energy loss deficit at high latitudes. So there is always a energy transport, heat transport happening by the meridional circulation in the atmosphere and the ocean, which we haven't looked at in detail, but we will look at again later on. But we know that the Hadley cell is doing some transport, but in the low latitudes, oceans are doing most of the transport. Once we go to the mid latitudes, in terms of the energy getting out of the tropics, you can see these tilted structures in both hemispheres. Okay, so if we want to look at eddy transports, in this case the momentum transport by the stationary eddy and the transient eddy, the simple idea of Starr and I think Noel maybe was that to be able to cross net momentum across or heat across a latitude, this is a latitude here in the northern hemisphere and southern hemisphere, you cannot have circular eddies because in that case U prime V prime will go north and come back south. So a circular eddy will not do any net transport across a latitude. So you will need these tilted structures where warm low latitude air is being advected northward or momentum is being advected northward by the eddies, and then a different structure is bringing it back south, so that you have greater transport northward than southward, and similarly here southward versus northward. So the troughs and the ridges here have to have the structure with the temperature lagging the momentum to create net transport of heat. So V star U star is greater than 0 here, and V star U star is greater than 0 here as well. So you have to transport momentum and you have to transport heat. That's the only way you can accomplish net northward transport, because as we will see, beyond the Hadley cell, the baroclinic instability doesn't leave really a very strong meridional mean circulation. There's a weak circulation which often we refer to as a Ferrel cell, and we call it as like a kinematic gear that connects the thermally direct polar cell and the thermally direct Hadley cell. It's not thermally direct, etc., etc., but essentially we'll derive expressions that show that these tilted structures are doing eddy transports to the northward poleward directions in both hemispheres. Okay, simple ideas, but just get used to the physics of it. We are kind of taking a very brief approach in terms of the equations. We didn't derive in detail the equations, but best be aware of the assumptions that go into the equations that we are using. Holton is a very good resource, a very detailed derivations there, and mid-latitude dynamics offers much more elegant solutions than the tropics, I would say. Okay.